I also hope this is not a complete waste of your time, that you learned something today. So, if you wonder where my accent is from, I'm Armenian. I came to the US to study when I was 20. And I studied for my undergraduate degree in Armenia, then did my PhD at Case Western in Cleveland, Ohio. Then I worked in London, Boston, Syracuse, and most recently, since 2006, I'm at Simon Fraser. And by trade, I'm a theoretical cosmologist. So what that means is that I'm not an astronomer. I use astronomy to learn about nature. So for me, while I admire astronomy and everything that astronomers do, for me astronomy is a laboratory, is a tool, which I can use to learn something about how the nature works. And my talk today will be about, it will be mostly historical. I'll try to give you a sense of how we physicists or cosmologists in this case, cosmology is just a branch of physics, what we learned about our universe and what we learned about gravity in the past 100 years. And also give you a flavor of what we're thinking about these days and what we can look forward to in the future. So this year happens to be 100th anniversary of Einstein's theory of general relativity. So this is a very important theory for many reasons. It's an extension of Newton's theory of gravity. So before that, there was a fairly solid theory of how gravity works, but not comprehensive enough to say how gravity works in all of the universe. So Newton's theory could explain very well how the moon goes around Earth and how Earth goes around the sun and why this will drop if I happen to drop it. But it could not, it didn't have the capacity to even address how the universe acts as a whole. And so the importance of Einstein's theory was that it, for the first time, provided a platform, a language, that we can use to talk about evolution of the universe. And by that, I mean space and time, and everything in it, that we, the planets, everything that happens to populate the universe. So these words of John Wheeler capture the essence of general relativity in its, very nicely. So it's, John Wheeler said that the essence of general relativity is that space-time tells matter how to move, and matter tells space-time how to curve. So it's the interplay of the two that together plays an important role in determining how the universe evolves. So Einstein was the first, in fact, to understand the importance of his own theory and tried to apply his theory to explain the universe. And he has very strong ideas about what the universe should be. So one thing you may know about Einstein or read about him, he didn't take experimental evidence very seriously. He had his own aesthetic reasons for doing things. He believed in certain principles of simplicity, symmetry, aesthetic principles that he thought nature should obey. And so he thought that the universe should be homogeneous, meaning there should be no special place anywhere in the universe, just like Copernican principle, but taken to a more broad platform. That he also didn't want the universe to have a beginning or end. He believed that it should be the same at all times, so that homogeneous in space and time. So same everywhere and at all times, so it has to be static. Now, as I'll show you in a minute, that forced him to conclude that it had to be closed and negative, and it had a negative cosmological constant. But that will become more clear in a second. And that didn't work out. And that actually turned out to be that his theory was correct, but his solution for the universe wasn't. And so, before I venture into explaining why Einstein was wrong, let me just introduce a couple of things that will appear once in, a few times in the talk, and there will be a couple of equations, but they're not very important. So, the universe, as it turns out, doesn't like to stay static. It likes to either expand or contract. And Einstein was right that the universe was homogeneous, especially homogeneous, that it's more or less the same everywhere if you look on large scales. It's inhomogeneous here because there's a table, and me, and you, and then it's inhomogeneous in the solar system because there's a lot of empty space and planets here and there. But if you look at huge things, like clusters of galaxies and bigger, basically clusters of galaxies look more or less the same there on the sky as they do more or less there on the sky. So the universe is really more or less homogeneous. It's statistically the same everywhere. And it likes to either expand or contract, if you believe Einstein's theory of general relativity. So expansion literally means that space expands. It's like having a rubber sheet and stretch it. So if you had galaxies painted on that rubber sheet or attached to it, they'll just get further apart. Now inside the galaxies, the space is not expanding because gravity holds the galaxy together. Just like the space between us and the sun is not growing because gravity is keeping us together. But the space between very far away objects, like distant galaxies, is indeed growing. And physicists use a function, A, which we call a scale factor, to describe that expansion. So if A is the same, constant, then the universe is static. So A could describe a distance between two arbitrary distant galaxies, and everything else can be expressed in terms of that number. So in an expanding universe, A would be increasing with time. So A comma T means A as a function of T. I assume no knowledge of mathematics on your part. And I apologize because I'm sure most of you do know mathematics, but I don't necessarily want to rely on it. And so A is a one number that we can remember. Another number that is important in talking about universe is its curvature. So what do we mean by curvature? The universe, in Einstein's theory, can be one of these three. It can be flat, it can be closed, which would mean positive curvature, or it's open, which is negative curvature. Now that can be a little bit difficult to comprehend if you're thinking about it first time. But I find one way of explaining it very efficient. So we know that if you take a triangle and paint it on a flat surface, the sum of the angles would be 180 degrees. Right? Now try painting it on a sphere. So on a sphere, I can actually have three angles that are all 90 degrees. Sorry, I don't have a picture of it, but you can probably imagine it. If I can always draw a triangle on a sphere that has 390 degrees. So we call a space flat if sum of the angles in a triangle is 180 degrees. That's what we call a flat space. And if it's more, then it's closed. It's curved positively. And if the sum is less than 180 degrees, then we call it open. So the space has that property that if you position three satellites in space and shine lasers, right, to form a triangle made of three satellites shining lasers at each other, and count the degrees inside the triangle, right? If it's 180 degrees, then the space is flat. And that's what happens to be the case with our universe. But that wasn't obvious at all. It's a measurement that we've made, and we know that as an experimental fact. Okay, now Einstein Einstein's theory gave us equations, so that's great. And before I write it in terms of mathematics, let me explain their essence. So Einstein's equations can tell us how the universe expands. The rate of expansion is determined by the density of matter in the universe, the curvature, whether it's closed, open, or flat, and whether it has a cosmological constant. So these three ingredients. It also tells us, it's a separate equation, can tell us how that expansion how can it accelerate or decelerate. And it depends on similar things, but not quite the same thing. It depends again on the cosmological constant, and it depends on the density and pressure of what's in the universe. Now, mathematically, I'll just put it out. So this is the two equations that communicate the same meaning. And what Einstein didn't like was the fact that the universe would have any kind of rate of expansion and any kind of acceleration. So he wanted to make these two equations equal to 0. Okay? We all know, at least you know that much. You have an equation that we want this to be 0 and that to be 0. So that's what Einstein did. He asked, what would it take for these both equations to be 0? And it turned out that he could do that. So to get two equations to be 0, if the universe was slightly curved, if it had a positive curvature, and if it had a cosmological constant that was slightly negative. So his universe was a bit not flat and had a weird thing in it, minus a negative cosmological constant, but it gave him a static universe. So it didn't work, because it turned out that even if you build such a universe mathematically, it wouldn't be stable. It's like trying to balance a pencil on its head. Yes, theoretically you can, but in practice it would never work. So Einstein essentially tried to balance a pencil on its head. But the moment you let go, the universe will either expand or contract. Okay? And that was pointed out by Russian astrophysicist and mathematician who lived basically who did this work during the dark years where the Russian Revolution was taking place, and he died soon afterwards. But he pointed out that there is this instability, and so this is translated means on the curvature of space. So what happened afterwards was the following. So the fact that the universe will either expand or contract as a consequence of Einstein's theory, that became apparent theoretically. So due to work of Friedman and also Georges Lemaitre, they established the fact that mathematically that's what should happen. But Einstein, again, he didn't like it and he didn't believe it. He called this abominable. Okay? He would not accept it. In parallel, there were developments in observations. And a few important things happened during that time that convinced Einstein to accept his theory. And actually, you should realize that at that time, in 1915, 100 years ago, scientists didn't know that there are other galaxies. All that was known was the Milky Way. Okay, so the fact that Einstein assumed that the universe should be homogeneous and isotropic is purely on aesthetic reasons. So all what that was known at that time was our own galaxies, and of course there were some sparkly points that they saw in the sky that looked strange. They didn't look like normal stars that would be part of the Milky Way, but they still didn't know that there were distant galaxies, that they were not inside the Milky Way. And so what happened between 1912 leading to late 1920s was it became apparent that some of the sparkly things that they saw in the sky were actually not inside the galaxy, and they were distant galaxies. They called them nebulae. Okay? And a particularly important breakthrough occurred due to work of Henrietta Leavitt, who discovered that certain types of stars, called Cepheid stars, could be used as standard candles because they pulsate in a way that's in a direct relationship to their luminosity. So if you know the period, you can tell what the brightness should be, and then by looking at the brightness, you can tell how far away it is, because if you know what it is at the nearby distance, then you can figure the brightness goes down as 1 over distance squared, so you can calculate how far they are. So they started using the Cepheids to determine how far these nebulae were, and it turned out they were really far away. Okay, so they discovered that there is more universe, and moreover, they discovered that this nebulae, the further they were, the faster they moved away from us. So they discovered that from the redshift. So different parts of those nebulae were redshifted by a different amount. And the further away they were, the more redshifted they were. So that was put together by Edwin Hubble, even though he was one of many astronomers who were making the case for this observation. He was the one who's credited for it because he put it together. Okay, so he came up with this very famous Hubble plot, which says that the distance is proportional to velocity. So the farther away a nebula is, a galaxy, the faster it moves. So Einstein, that convinced Einstein, and that he called his static universe his biggest blunder. And that's a famous word, famous phrase attributed to Einstein when people talk about cosmological constants specifically. So it's so often misunderstood. I think he called his biggest blunder not the fact that he had to come up with a cosmological constant, but the fact that he ignored his own prediction of his own theory, that it had to be expanding more. Now, if you are a thinking person and you're given a fact that the universe is expanding, then you immediately can come to some really powerful conclusions. What does it mean that the universe is expanding? It means that things are moving further away from each other. So in physics, if you take a gas, if you probably had some high school physics, and if you take a volume of gas and you're expanding, it cools down. So an expanding universe will be cooling down because the distance between stuff in it is growing, and temperature is related to the motion. It's due to the motion of ingredients in your gas, or in this case the universe. But if it's getting cooler now, it means that in the past it was hotter. And so if you extrapolate, if you look back in time, if you think what was back in time, it means that the universe was increasingly hot as you go back. And it was increasingly dense as well. So it was a really violent place early on. So galaxies and planets wouldn't be able to exist because they would constantly hit against each other. In fact, atoms couldn't exist because they would hit each other and break up into electrons and protons. And protons wouldn't exist because they would hit each other and break up into quarks. So the early universe was a violent place, very hot, and it had no structure. It was a soup of particles, the most basic elementary particles. And that's just a thought exercise. It's somebody told you the universe is expanding, and we just used our knowledge of physics to sort of imagine what the universe was a long time ago. Now, if you wanted to test this, if you wanted to turn it into real science, you would have to actually test it on an experiment. Unfortunately, there is a way to see, and that's what people like me do. We try to see evidence of these things on the sky and compare it to our theoretical predictions with some precision. So the evidence comes from the fact that when you look deep into space, you're looking back in time. If you have thought about this, and this is obvious to you, sorry for stating the obvious. If you haven't, then it follows from the fact that light takes time to travel. So if I'm looking at you, I don't see you the way you are this instant. I see you some time ago. Because it took some time for the light from you to come to me, your image. So I see you in the past. In space, that's taken to an extreme. When you look at through your telescope at some star, you don't see it the way it is today. You see maybe a few light years ago. Okay? Galaxies, some galaxies we use in our studies, we're looking at how they were billions of years ago. Okay? So this is what universe is like when you start looking deep into space. This is a cartoon. It's not real, obviously. But what is this picture showing? So you're here and you're looking out into space. So if you look not very far away, the space is still about the same age as us, maybe a few hundreds of million years different or a billion years different. It's not that different. So you see objects similar to what our galaxy is and its contents. But if you look further away, you look so far back that galaxies and stars haven't had time to form. So you see some diffuse gas which hasn't had time to congregate and form stars. If you look further away, you see darkness, nothing. Because there's nothing at that time to shine light. To shine light, you need to form a star. And if star hasn't formed, there is no light. And then at some point you see a wall. And what is that wall? It's a transition between a transparent universe and opaque universe. So if you look this far back, you're looking at the time when the density of that primordial soup was so high that you cannot see through. Okay, so there is a limit to what we can see with light, with electromagnetic waves, with radio waves, or any kind of electromagnetism. Okay, there is a limit. And this line corresponds, it's 14 billion years ago, okay? Or if you count from the Big Bang, it's 400,000 years after the Big Bang. It's called the surface of last scattering. And this surface, so looking at this surface, at the transition from transparent to opaque, has been the most important thing in cosmology. That we learned so much by just studying its properties that it just gave the whole field a completely different type of significance. So what is that surface? It's basically radiation which fills the space. It's here in this room. It's in old TV sets before they became all liquid crystal and etc. So about 5 to 10% of the white noise is radiation that comes from that last scattering surface. At that time it was 3,000 Kelvin hot, roughly 3,000 degrees Celsius hot. Okay. But by the time it reaches to us, because the universe is expanding, that light cools, the temperature cools down. So today it is only 3 Kelvin, minus 270 degrees Celsius. And this light was around, and the sensitivity of radars and telescopes has been pretty good since 40s to actually see this, and people have been seeing it. Most famously, perhaps the first one was Andrew McKellar, who was the president of RASC, in fact, in 1959. But he was also a professional astronomer, spent most of his life working at the DAO, the observatory in Victoria. So he observed what he called temperature of space by looking some absorption lines that were not quite consistent with zero temperature around them. That was largely ignored because there was a war going on, and he himself took part in the war. So there were other sightings of this radiation, but so people would see it, they would talk about it, but nothing would come out of it. So it took some time before it was sort of properly measured and recognized. And this is perhaps the strangest Nobel Prize to my taste. So the story is that these two engineers, Lindsay and Wilson, were testing a radar, which was not for astronomy, it was a radar. Okay? And they observed that they were trying to calibrate it, and no matter where they pointed it, they found excess noise. And they were puzzled by that. And at some point, they heard that people nearby at Princeton University were actually building a similar machine, similar radar, to do some astronomy. Okay? And when they communicated with them, people at Princeton realized that this could be this cosmic microwave background, this light. And so this paper was the second shortest paper that won a Nobel Prize. If you read it, it doesn't say anything about cosmology. It's mostly about, we have a radar, we point it everywhere, and we can't figure out what's going on with noise. And then here they say that a possible explanation of this given by these people, and that's the Princeton group. There's no reference to space otherwise. So anyway. They won the Nobel Prize. And today, that's measured to exquisite precision. This is what you get if you point your radar or your antenna at every point on the sky and record the intensity of that radiation. And intensity can be converted to temperature, and we can paint it with color. So this is not the actual temperature, it's departures from average. So average temperature is 3 Kelvin. And the colors here mean difference from the average. So they are about 1 part in 100,000. The measurement is extremely accurate and precise. And just like we make a map of the Earth on a flat map, right? We can't see behind the sphere. We flatten it and we study CMB in a flat and distorted way. So we can make a map of the microwave temperature. And there was another Nobel Prize awarded to this by due to Toby satellite. So the leaders of that collaboration, George Smoot and Joe Mather, got the Nobel Prize. And the significance of that was precisely to detect that not only there is this 3 Kelvin radiation surrounding us, but it also is not perfectly homogeneous, that there are this 1 part in 100,000 fluctuations in its temperature. And they measured them, and that was very important. So that was the state of the universe in 1992. So people knew that the universe was expanding. Measurements of this microwave background confirmed that the universe was hot in the past. That's a powerful measurement for the history of humanity, if you wish. People got convinced that indeed in the past the universe was hot. So it's a very profound realization, but there was no sense of there were many puzzles, and there was no sense of universe actually accelerating. We knew it was expanding, but no talk about accelerating. So that came later. So the state of cosmology in the 90s was a bit obscure, just like the presidents. I actually have a video. When I was a grad student in the late 90s, so there was a press conference when these two came out of the White House, completely drunk. And it was live. And I saw that, and I taped it, and I still have it. It's hilarious. They just stand by the microphones and laugh. So the cosmology in the 90s was in a bit of a mess. Why? Because, first of all, people would use all kinds of methods to estimate how much matter there is in the universe. Not just visible matter, but any kind of matter. Okay? Turned out that only 10 to 50%, that used to be the error at that time, could be, all of the energy in the universe could be matter. So there was some other form of energy that was missing. And out of that matter, only 5% would be normal, what we would call visible normal matter that we're made of. The rest would be dark matter. And that's actually still unknown. Also, we didn't know if the universe is flat or open. And to compound this issue, people would observe stars that were older than the age of the universe. If you naively used the knowledge of the universe at that time to calculate its age. So clearly there was something wrong with the calculation of the age of the universe. Okay? So based on all these facts, putting it all together, just circumstantial evidence, some people, famous cosmologists, in fact Lawrence Krauss was the chair of the department while I was a student, and so I remember him bouncing around saying there must be a cosmological constant, must be a cosmological constant, based on all these facts. So basically, these two made a case that there must be dark energy that would make the universe accelerate, and the best candidate for that would be cosmological constant. And the evidence came in 1998 from observations of distant supernovae. So they two groups of astronomers measured magnitude of supernovae at different redshifts and compared that to prediction in non-accelerating universe versus accelerating universe, and the accelerating universe matched it much better. And that was a big discovery. So these are the three people who got the Nobel Prize. And let me explain, it's kind of interesting how discoveries in science happen. Sometimes it takes a good idea. But technology would be there for a while, but sometimes it takes a great idea to sort of make a breakthrough. So supernova, as many of you I'm sure know, are very good standard candles. First, they are very bright things. So even if they happen in a faraway galaxy, they can outshine a galaxy for weeks. So it's a very bright event. And it lasts a long time. And then supernovae occur when, let's say, two stars orbit each other, one of them dies, falls into another, and there's a big explosion. It's a whole different story. If you hope to see a supernova explosion in our own galaxy, then you have to wait a very long time. So on average, they happen once every 500 years. So it's been documented. There's some sightings by Chinese astronomers. Brahe observed one in 1572. And what makes them nice is that they're quite like each other. So they're standard candles. The explosions, particularly for type 1a supernovae, happen in the same way. For the way they explode and the way the light curve evolves is quite reliable. So that, just like Cepheid variables, Cepheid stars were used to determine the Hubble expansion rate, supernovae could be used for a similar purpose. And so this is say how it works. The time scale for the explosion, as I said, is weeks. And so this is an explosion. This is in optical. You can see it happening in some remote place. And you can study the luminosity as a function of time, and also the spectrum. So the spectrum also evolves with time. And so these things are quite uniform. For example, the sequence of colors and the way the shape evolves is same to some approximation for all supernovae type 1a. So you can use your knowledge of one supernova nearby to determine how far another supernova is. And so what was this idea that led to the Nobel Prize? It was Saul Perlmutter's idea. He came up with this supernova on-demand mechanism. It was a management sort of breakthrough, more than technological or sort of particular physics breakthrough. So he realized that the techniques used to observe supernova were very expensive. You can't just point on the sky somewhere and wait for a supernova to occur. Okay? That's just not going to happen. Instead, he proposed that you use big wide field surveys that look not at individual stars or explosions, but just many galaxies at the same time with a wide field view. Okay? Use that to detect if there is some supernova. And then point a very accurate, so the moment it's observed, you call up your friend somewhere else and say, point at these coordinates, there is something going on, and measure that with great accuracy. So they had this sort of a chain of command set up, where every sort of 2-3 weeks they would spend 2-3 nights recording wide field view of the sky, and have their friends on a standby with accurate spectroscopic cameras ready to follow up. And using this kind of efficient machinery, in a few years they measured about 40 supernovae. Before that, there were only few. People just waited for the luck. So I think Saul Perlmutter was the one most deserving of this Nobel Prize. I don't know much about, obviously Nobel Committee took everything to come, but this other group from Australia, they basically followed up and did the same thing in parallel. And they simultaneously published the papers. So the key information for that is knowing the redshift of the host galaxy, which you can get from spectroscopy, just how much the spectral lines of the galaxy shifted, and you use the observed luminosity to determine the distance, because observed luminosity is intrinsic luminosity of the supernova divided by 4 pi distance squared. So you use this to calculate the distance. And then you have an equation based on Einstein's theory that tells you how this distance is related to the amount of matter, amount of dark energy, and all that stuff. And if you want to see, that's the equation. So it's just some equation that tells you that if you have some amount of matter, some amount of cosmological constant, Hubble constant, and redshift, predicts the distance. So you see what you observe, and you try to match this equation, and you learn about what these numbers are. And that's what these people did, and they found that the best match, the best fit, is when omega is here, somewhere in this. This was the 1998. So basically, clearly, the zero cosmological constant was ruled out. So they discovered that there must be some positive cosmological constant. Okay, now, so since 1998, it's been known that we live in an accelerating universe. So lambda is back, universe is accelerating. I'll skip this. So that means that in the future it will expand exponentially fast. If you know what exponential is, so it's very fast. Okay? And so our future is quite bleak in that sense that everything we see nearby will start disappearing from sight very quickly. And since 1998, the evidence grew stronger. So we've had WMAP and Planck satellites that were sent into space to measure cosmic microwave background at microwave sky with exquisite precision. Surveys like Sloan Digital Sky Survey measure millions, actually hundreds of millions of galaxy redshifts. And now, instead of having 40 or 50 supernova, we have close to 1,000 supernovae. So and all of that evidence supports the fact that the universe is accelerating, and so that's why the Nobel Prize was awarded. It was stronger. And this is, just to give you a flavor, this is a measurement from Planck satellite of the microwave background spectrum. It tells you how much the anisotropy or inhomogeneity there is in microwave sky on a given angular scale. So it's a spectrum. And so the large angles are here, small angles are here, but these points include error bars. They're just so small that you can't see them. So it's an exquisite measurement. And from the structure, the fit is our theory, and it fits very well. And from the structure of these peaks and all that detail of that plot, you learn various things. You learn words that I'm not going to explain, but I will tell you what they mean. But in particular, the one thing worth mentioning, that the fact that this peak and this peak are different height means there is dark matter. Okay? So it's, if you want, you can ask me later why. But I'll just move on. So you learn a lot from this plot. And if you put it together, you can compare what you learn from CMB to what inflation predicts. Inflation is a theory of early universe according to which universe, when it was very young, it expanded exponentially fast. And it makes some amazing predictions. And predictions match perfectly to what we see on the sky. I'm not a big fan of inflation, but I had to accept it at some point because the evidence was so strong. You can ask me about that too. And this is what you would see in a typical sort of a WMAP or Planck paper. This is from WMAP. This is numbers you measure by studying these plots. And you see that uncertainty in this number. So you measure, for example, that amount of dark energy of cosmological constant is 72%, 71.9%, plus minus 1.4%. So we don't just know there is cosmological constant, we know it's 72% and uncertainty is very small. So you could say that with numbers measured so well, we have a very good working model of the universe. And if we take the CMB, right, so if you think of that image that we see as some initial state of the universe, the inhomogeneities, the colors on that picture represent actual inhomogeneities in the density of things at that time. So imagine putting it in a computer and letting it run in time. So what will happen is that places that were slightly more dense would congregate, would be more likely to collapse through gravitational attraction. And those places would be more likely to form things like galaxies and stars. And so this is a simulation of that. So you can see that in this picture, blue is denser. So things grow, eventually particles group due to gravity, you form stars, you form all kinds of structures. Okay, and gradually the universe becomes the way it is. All of this is purely due to gravity. You start with some initial inhomogeneities that exist in the primordial soup, let it be, and they collapse and form the universe as we see. So what the point of showing this is this is not how we do science, by the way, we do slightly differently, but the message is the same. What we do is we study, we try to predict what the universe should look like today, given what we see in the CMB. And the agreement is very good. But it only is good if there is dark matter. Okay, so for that to happen, it won't happen if matter is the usual kind. So dark matter is a different story, and it was first sort of talked about by Fritz Zwicky. What he saw was that when he looked at the motion of galaxies in coma cluster, he observed that the mass of the stuff that should be in a coma cluster to make that motion, the velocity is consistent with physics, that the mass should be 400 times larger than what is seen. So there was more matter there, but it was invisible. And he used this word dark matter in German. Yeah. He also was the first to tell us how to see dark matter. So we cannot see it with light, but we could see it because it has gravity. And gravity acts as a lens. So even though you cannot see it, you could see it by the way it deflects other light. And so that's the idea. That's again prediction of Einstein's theory. So Newton's theory would have nothing to say about this, but Einstein's theory predicted that anything that has gravity or energy would actually act as a lens. It would change the way the light propagates. So there's some famous images from Hubble telescope. Here what we see is images of some distant galaxies that are lens distorted by a massive cluster along the line of sight. The cluster itself is made largely of dark matter. You can see through it. Dark matter is invisible, but it has a lot of mass. And so it acts just like a lens, just like putting a lens in front of the distant images. And recently there's been quite a remarkable observation, and you probably heard about it from news. It's not even recent anymore, it's been almost 10 years. But it's a bullet cluster, where they managed to use 3 types of observations. Optical, just by looking at light, lensing, which they call dark matter. So they used lensing reconstructions, and X-ray to see what's going on here. And they came up with this picture. So in optical, you see a bunch of shiny things. With lensing, you infer existence of a lot of mass. So the blue denotes the density of dark matter. That's invisible to an eye, but from the way it lenses stuff, you can infer its existence. An X-ray This is sensitive to hot gas. Things that, again, you don't see with your eye, but it's real matter. It just emits in X-ray. And this is a simulation of what happens if two clusters of galaxies collide. So suppose you have two clusters of galaxies collide. So it has dark matter, which is blue, and hot gas, which is red. As they collide, dark matter doesn't see another dark matter. It's just that they don't interact. They just go through each other. But the gas sees each other because they have Coulomb electric forces slowing them down. So the gas gets slowed down and dark matter goes through. And this is, if you look at this, which is a numerical simulation from theory to prediction to what you see on the sky, amazingly similar. So it's again good reason to think that there's something interesting going on. So again, does it mean that we have a working cosmological model? Indeed, we're able to simulate and predict a lot of things. And all we need is a few ingredients, like inflation for the origin of the universe as we see. We need existence of dark matter and dark energy, such as cosmological constant. Yeah, there is only a minor problem in this, is that we basically don't know anything about these three things. Okay, so if you're a cosmologist and you want to write a ground proposal, right? There are two ways you can go about it. You can say, you say we discovered dark energy, or you could say we don't know what 70% of the universe is. But dark energy is a big problem. So let me now talk a bit about that. So there is a popular viewpoint among many of my colleagues that basically acceleration is indeed beyond reasonable doubt. There's just evidence on the sky and it's been confirmed. The cosmological constant is part of Einstein's theory and it works. There is no compelling alternative. I myself tried to come up with alternatives. There are many people trying, but they create more problems than they solve. And if they don't create problems, then they become the cosmological constant. So they either create problems or they're indistinguishable. And lambda, as I told you, we measured it to 1%. So they say, okay, that's it. That subject is closed. They're not interested. Now, I don't quite like that perspective, even though that's not a small number. I would say about half of the cosmologists would think that way. Now, the different viewpoint to which I personally subscribe is that there is a big problem in physics. It's not a problem even with cosmology. It's more general than that. It's a problem with gravity and quantum mechanics. Quantum mechanics predicts that there is energy in empty space. And it's not just a theoretical prediction. That energy has been measured in earthly experiments. We know it's there. There is energy in empty space. But Einstein's theory of gravity says that every kind of energy should have gravity. Then you say, fine, let's calculate how much energy there is in empty space. Let's see how much gravity it should have. It's wrong by a factor of 10 to the 120. So it's a big problem. And that problem, it doesn't have a solution. It's been known for a while. It's been around, and it's gotten so old that people started to ignore it. It's like the annoying neighbor or something. So, but when this lambda was measured, when the cosmological constant was measured, the thing about vacuum is that mathematically, energy in a vacuum is the same as the cosmological constant. The way it appears in your equations is the same. So when cosmological acceleration was measured, we measured this cosmological constant, it's equivalent to measuring energy in a vacuum. But it's much, 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 much smaller than that number. And so the question came back. So now we have to explain not only why the quantum vacuum doesn't gravitate, but why it gravitates so weakly. So it became a new problem. So that problem needs a solution. And it need not necessarily come from astronomy. It may be just that somebody needs a good idea, like Einstein had at some point. It needs a theoretical breakthrough more than anything. Dark matter, obviously, is dark because we don't know anything about it. We just know there is matter that's invisible. And also gravity, as good as that theory is, it's really not been tested outside our solar system. Really, it hasn't been tested. So if you think about it, within solar system, yes, we send all kinds of probes, measurements, it works beautifully. But outside, we start needing dark matter. So if you want to explain how stars move inside a galaxy, they don't move the way Einstein predicts if you don't add some dark matter to it. Same with this universe. And finally, astronomers have only mapped a small fraction of the space that is available to us for studying. So as I said in the beginning, we use cosmologies, astronomy as a laboratory. And there is a finite volume that we can see. We can only see things inside our horizon. It's about 14 billion light years each side. Okay? That's it. We can't see behind it. So why don't we see everything? We can, in principle, but we've only seen a tiny fraction of it so far. So there is a lot of effort put nowadays into trying to see the rest of it. So there is a survey that started, it's been in the news recently because they published first results. There is approved, fully funded European satellite called Euclid that's going to go hopefully somewhere in 5 to 6 years and measure a lot of galaxies and lensing of galaxies, and we'll learn a lot of great stuff about dark energy from that. It's 9 o'clock. So there is also large synoptic service telescope, which is an ambitious project that's going to happen. It's an optical instrument. And why all these things are necessary, this is just to give you an idea. So today, we can measure this surface really well. Okay, that's the CMB, and it gives us a plot like that. We can also map some galaxies nearby, such as those measured by Sloan Digital Sky Survey, and it also gives us plots, okay, which we can compare to our theory. But the resolution we have in distance to these galaxies is not great. Okay? That's why I drew it as a donut. This is my donut. What I will try to represent is that we can't tell radial distance very well. Now what will happen in the future, the radial not only will have this temperature and in addition to that polarization, which is a whole different story, we'll measure this distribution of galaxies and everything there with exquisite accuracy in radial distance, in redshift. So we'll be able to do tomography. It's like putting a universe through a CT scan. We will know what happened at each instant in history back in time. Now we can sort of tell roughly. When you look back, plus minus million, 100 million years in history. Now we'll slice it up. And that allows you to see how the universe evolved in detail. And compare that to predictions of, in this case, Einstein's equations. So that will be a test of Einstein's equations. Do they evolve exactly, do they predict exactly the same evolution as we see after doing the CT scan? And we'll measure lots of different things. The visible matter, gravitational lensing, and other things too. There's 21 centimeter, which looks at neutral hydrogen, 21 centimeter lines. So what we want to learn from this is a few things. I personally want to know, is data really consistent with the cosmological constant? Are there any funny things going on? And also, is it consistent with the equations of general relativity? So at every time step, are they agreeing or not? And also, if we know general relativity is not complete. Either quantum mechanics or general relativity, or both, are incomplete because they don't agree with each other. They have this discrepancy of 10 to the 120. So if there are alternative theories out there, what are the constraints? How much freedom there is for alternative theories? So there are many, many theories. This is a zoo of theories. They're just funny names, like Galileans, the horn. What other funny names? Doesn't it? Extra dimensions and so. So we have our wish list for what such an alternative theory should be. Yeah, so it should have all kinds of nice things: solve the dark matter problem, solve the dark energy problem, and after all that, have something we can see that will tell us it's not just the same theory. So we recently organized a meeting in Vancouver where we brought all kinds of people to discuss how we can test gravity, and not just with astronomy, but with every kind of experiment. So that's my claim of fame. I was in the 24 newspaper. Well, actually, that was a great meeting, and we will be doing it every 2 years. So I'm almost finished. Let me tell you at the end exactly what would be a smoking gun signature that we would be looking for to test this gravity. As I told you earlier, Einstein's theory predicts how space-time should curve and how matter should move in response to the curvature. And it predicts that it's that curvature and the gravitational potential is what causes gravitational force. So they are actually equal to each other. So the curvature of space locally somewhere, when you have a mass, it curves the space, right? And it creates a gravitational potential. And Einstein says that the curvature of that potential well should be exactly the same as the value of that potential. It's just a prediction of Einstein. In modified gravity, pretty much every theory on that theory zoo diagram, it's not the case. So a very interesting way to look at it would be see if we can detect the difference between curvature and the gravitational potential. So how are we going to do that? We know that light, so gravity bends light. I showed you earlier an image of gravitational lensing. But strictly speaking, this light, or photons, they feel both. They feel curvature and the gravitational potential. So these two things mathematically are not the same. In Einstein's theory they are, but in general they are not. And so photon feels the average of this curvature and the potential. But matter, normal matter, in this case galaxy for example, when it travels, it feels just the gravitational potential. So a key test of Einstein's theory would be to compare the motion of a galaxy in a given environment and the lensing that that environment produces of other images. So the lensing is what bends light, and it's the curvature plus potential. While the galaxy responds just to the potential part of it. So Einstein predicts that they should be the same. So if we observe the motion of galaxies, we could predict what the lensing should look like. Or if we observe lensing, we would predict what the galaxy motion should be like. But if there is some inconsistency between them, okay, then that would be a smoking gun of something going wrong with Einstein's theory. And that's why there is a lot of effort in this field. This effort to measure lensing distortions of distant galaxy images. So they would probe the geodesics of light, how light propagates. And also there is this massive redshift surveys of galaxies that would determine motion, measure galactic motion, and compare the two. So this is the kind of banana plots that I deal with in my physicist life. So these two numbers mean something like the strength of the curvature and the strength of the potential. Okay, or the departure from Einstein's prediction. So if they're both zero, it means GR is correct. General relativity is correct, and they nicely overlap. So one banana you get from weak lensing, the other banana you get from galactic motion. Okay, they nicely overlap. So the position of the overlap tells you what their values are, and if they are anything but zero, it means Einstein is wrong. So far Einstein is correct, but there is a lot of freedom here, and these things will keep shrinking as the data comes. And the question is, where will they come? If they come somewhere here, then we'll have maybe something to talk about. Okay, so you survived through my talk. To conclude, I'll just summarize quickly. So, because there is a Nobel Prize, we can say that cosmic acceleration is beyond reasonable doubt. Otherwise, there wouldn't be a Nobel Prize. And there is still something to keep an open mind about the General Relativity has not been seriously tested outside the solar system, and we don't know what dark energy is. We don't know how vacuum gravitates, is what dark matter is, and there is a lot of effort. The good news is that there is plenty of funded giant observational instruments, and there is a lot of room for theoretical discovery, and something can happen anytime. Somebody may just have a eureka moment and solve the dark energy problem. Thank you.
Anybody have any questions? There we go.
Oui.
Eddie.
There used to be a theory that the universe would expand so much, and then, like an elastic band, would come back within itself. But according to what you're saying, there isn't enough physical matter to give it a strong enough gravitational field to pull it back?
Yes.
That's
Well, more, it's not that there is not enough matter, there is additional energy, which is this dark energy, which has repulsive gravity. So it's not very important when the universe is dense, because normal matter overwhelms it. It's when the universe is denser, so the usual type of matter dominates, and it acts like normal gravity. And if that was everything there was in the universe, then, as you said, it would eventually stop expanding and collapse back. The gravity would pull things back. But because there is this additional cosmological constant or dark energy component, it has negative gravity. So when the density of matter becomes low, dark energy takes over and starts inflating it. So there is this slowdown. We've measured that. Well, not me personally, other people. They trace the expansion of the universe through that. So as it was slowing down, and it was, if there was all to it, it would collapse. But then suddenly starts accelerating.
Could we see the theory zoo again? I was interested in that.
Sure.
The zoo of theories. Oh,
There it is, yeah. Okay.
where's Lee Smolin on that?
Ah,
The time guy. Is he on there somewhere?
this small, let me have a look.
Where would he be? He was doing quantum gravity or something.
Yeah, see, he's not here. So this Smolin is not here.
No? Quantum gravity? I don't know.
Well, quantum gravity, there's no sort of a complete theory of quantum gravity. It's a set of trials, but nothing that amount to full theory. Yeah.
Your conclusion is to stay tuned there. I'm interested in serendipity
Yeah.
and the theory of unintended consequences. I want to ask you about CERN.
CERN,
The Hadron Collider. Are you at all concerned about what they're actually doing there and what they might create?
No?
Good. I'm glad to hear that.
Why should it? Because of
Well, perhaps we
black
can
hole?
create the Big Bang again.
No, that's yeah.
Not
So that's highly unlikely, if at all possible.
Yeah, I've been reading about the electric universe.
Which universe?
Electric
Electric?
universe.
Okay.
And basically is another theory, I guess, that we're trying to put one idea on the whole universe, which is controlled by electricity creates gravity. And well, this is an idea of the whole universe, an electric universe. So there would be no Big Bang.
familiar with that universe. Sounds interesting.
I have a quick question. They are starting to develop telescopes that can detect neutrinos, which are really hard to detect because they hardly interact with anything. Is there any way that that sort of technology is going to help in the work that you're doing? Because those will travel right through the universe from the farthest reaches.
Yeah. So there are sort of two ways in which this can be used. There is, just like we have this cosmic microwave background, there is also cosmic neutrino background. Except neutrinos can pass through that transition between transparent and opaque. So this transition from transparent to opaque for neutrinos is at basically redshift, which is the roughly million times higher than the redshift of that transition. So it's going 1 second after Big Bang, if we could measure. Okay? But it's a big if. And the experiments they're building will not measure. But maybe in the future they will be able to do that. But what these experiments will measure is neutrino masses better. So we know, so in particle theory at this moment, neutrinos are assumed to have no mass. They are massless in theory, but experimentally they're measured and they're known to have a mass, very tiny, but a mass. And there is no theory for that. And knowing what mass is exactly and how it is will affect cosmology, because our theories of this, how the universe behaves, depends on what's in it. So if neutrinos have mass, some of these things should change. Not a lot, but a bit, but maybe it could be important.
Okay.
Yeah.
Another question? Yes?
What is your speculation on the moment before the Big Bang?
The moment.
Before?
Yeah. The moment. So your question includes an assumption that first there was a Big Bang, and second that there was a moment, and there was even a before.
Your whole presentation assumes there was a Big
No, that's a
Bang.
good question, because there is the word Big Bang was actually, I don't know if you know, but it was invented by Fred Hoyle, who didn't believe in expanding universe. It was sort of a label that he attached to something he didn't like. And there is a lot of misconception of what Big Bang is. So, from a physicist's perspective, all we know is that the universe in the past was very dense and hot. So, mathematically, the density goes to infinity if you write an equation. But whether that means that all the universe was a point, that's not at all obvious at all. It could be still infinite, but infinitely dense. In fact, all of the theories we have right now, that's the state of understanding, that there was no sense in which there was a point. It was just much denser. And also, we don't actually have a theory that could describe that moment, and not yet alone before. So we can only talk seriously about early time when things got dense up to a certain density. It's called Planck density. Above that density, the physics breaks down, and there is nothing we can say.
So it probably would be better to not frame it as a Big Bang.
The word Big Bang, well, if you already know what it means, it's fine. It's a label.
Well, except for it's a confining.
Yeah,
concept.
but there is somehow, maybe from some book in popular literature, came this notion that everything came from a point, and there was a bang. Yeah, that's not quite what we think of it.
Based on the CMB, whatever whatever it is, you can go back in time 13.7 billion years, and you know that prior to that there was this radiation soup, you call it a soup.
Yeah.
Right?
Yeah.
And something. And it could have been the static universe that Einstein's referring to. That could be the substratum from which everything is. And
You mean that?
It could, I mean, you don't even really, none of us really know anything. Really.
Saying that even though it's expanding now, if you take it sufficiently back far back in time, it could approach some static state.
It could be
Yeah,
like
oh.
a boiling pot.
Maybe.
And then when it quits boiling, it just comes to some, it subsides. It's like an ocean.
Okay, one more question? And then if you have questions, he'll be around for a while we are taking down, so.
So if we have a universe that we can see 14 billion light years out into the past, and if the speed at which the universe is expanding is going to become exponential, how long will it be before we are living in darkness?
Well, we will live in darkness when the sun runs out of
Oh,
fuel.
yes, of course.
And that's not affected by exponential expansion. We are
Sure.
confined by each other's gravity. When the sun runs out, it will explode or something will happen and we will die. But the galaxy, we will stop seeing other galaxies. Then the question is, when will we stop seeing other galaxies? We will stop seeing CMB.
So is it 14 billion light years, or is it?
When, I've seen, it's on the order of between 5 to 10 billion years. Something, it's in billions of years.
Not light years?
Oh, no, years.
Years.
No, it's in, you're asking how long it will take?
Right.
Just, years. Light years is a distance.
Okay.
So,
Okay, good.
Okay, wait, you gotta say that again. Are you saying in like 5 billion years or 5 billion
or
light
something
years?
of that order. Yes.
Oh, whoa, you mean like the same? I mean, that's at least something we can relate to, right? The
Of
Earth
course,
is
yeah.
like, I don't know, 5 billion years or something.
Well, we see 5 billion, we see 14 billion years back.
Yeah. But you're saying that in 5 billion years or so, we could not see, and we could be, if we were still around, whatever, nothing, no stars.
We could see stars inside our Milky Way if there's still, that's a separate process. Because things in the galaxy is gravitationally bound to each other, so to the black hole in the galaxy and all that gravity. But
Yeah.
other galaxies are not bound to us.
All right, thank you very much. That was great.